Hello, I'm John Durrant, and may the Force be with you. In this video, I'll talk about one of my Star Wars inspired projects, an animated Saber wall light, using an RP2040 board from WIZnet. WIZnet is a manufacturer of microcontroller boards and adapters for IoT projects. They recently released the WizFi360 EVB Pico board, and were kind enough to offer me an evaluation board. I've decided to try an IoT controller wall lamp project inspired by Star Wars. The concept here is for a wall light for my hall, which is a bit dark. Each wall light should be configurable with blade color. It should animate the turn on and turn off, so yes, it can look like a lightsaber, but also like a discharging wand or another animation sequence. There'll be a local activation switch on each device to turn on or off the light. It will also turn on if it detects a person with a PIR sensor in the handle. Finally, it will turn off after a period of time. This device should be configurable via IoT. By that I mean it will connect to my local MQTT broker. It should also synchronize across devices, turning on and off the other Sabers. So when one detects motion, they all turn on. The project is available on GitHub under MIT license, so you can copy and adapt it if you want. I'll put the link in the video description. Let's take a look at the WizFi EVB Pico board. This isn't a full review, but just an introduction to the device. If you'd like a full review, then please leave me a message below. Of course, like this video and subscribe to my channel. This board is based on the RP2040 processor from Raspberry Pi. It has the same pinouts as the Raspberry Pi Pico. This is handy for any Pico hats you are using. Like the Pico, it has a single wire debug port, SWD, for code loading and debugging. Unlike the Pico, it has both a boot select button and a reset button on board. I like this. It saves me putting additional switches on my projects. Wi-Fi is provided on the board using the WizFi360 coprocessor. This appears to be some sort of ESP chip providing Wi-Fi. It connects to the RP2040 via a serial interface. So the board is a little bit bigger than a standard Pico or a Pico W. It's got an RP2040 processor, 16 megabits of flash memory, Wi-Fi on 2.4 GHz, Wi-Fi station and soft AP on both modes can be activated on the device. It uses serial AT commands, much like the ESP processors running ESP-AT. Not identical though, there are some differences in the AT commands. It provides TCP server and TCP client and UDP sockets. Has a unique MAC address. It's CE and FCC certified, and of course we've got that SWD port. Wi-Fi 360 is connected to the RP2040 using UART2 on the device. This ties up pins 6 and 7. Hardware flow control is possible, which would tie up 2 more pins, but isn't mandatory. Reset for the Wi-Fi 360 is on pin 26, which ties up GPIO 22. There are a lot more GPIO pads on the device though, so this isn't really a major issue. Let's take a look at the project's hardware and electronics. A few components are needed for the project. The electronics for the project are generally very available. So is the acrylic tube that I used for the blade. The handle and mount for the tube was 3D printed though, but I've included the 3D models with the project. Quick health warning here. The project uses a relatively safe 5 volts. Hooray! It does though draw 5 amps of power. That's enough to cause significant heat and to burn wires and insulation. The The project also uses electrolyte capacitors, which will explode if connected the wrong way round. Please make sure you know what you are doing. Take precautions and double check. While designing the project, I had one of those heart-stopping moments when magic smoke drifted across my desk. I thought I killed the microcontroller. Fortunately, I had not. The smoke was coming from the insulation on my power wire, not rated for 5 amps, which was getting very hot. The full schematic diagram is included with the project source code. I'm going to talk through this in pieces. Firstly, the blade itself. This is a 1 meter strip of 144 WS2812B LEDs. It's connected into my logic level shift converter via a 300 ohm resistor, as required in the spec. To reliably use 144 LEDs, I do need to use 5 volts and not cheat with a 3.3 volt signal, as I do in some of my projects. The logic level shift converter is a bit overkill, I agree, for one channel, single direction, but it's cheap and reliable. I use a 1000 microfarad capacitor on the LED strip to prevent brownout of the RP2040. Jumping from full off to full on of the LEDs causes a spike that can cause the RP2040 to reset without this capacitor. I was testing using 5 volts and an 8 amp power supply to protect the board, and my nervousness around potentially heating to 5 amps causing me to design a 5 amp fuse and a 100°C thermal fuse into the project. So if it gets warm, it will cut the power before it catches fire, I hope. We connected a SPST switch in pull down mode into GP18 to turn on or off the lamp. Then the AM312 as a PIR to also turn on the lamp using GP16. I had some problems with false detects due to instability in power and random signals, probably from the Wi-Fi. So I placed some smoothing and decoupling capacitors around the AM312. I want to know the status of the device. Is it connected to Wi-Fi or MQTT broker? Is it sending data, etc.? So I used an RGB LED connected to GP3, 11 and 13. This somewhat random choice of pads is due to me adapting a board built for another project. Finally, I like to use a pulse LED to show that the board is running okay. This is on GP12. So I've adapted a previous board, and you can see this on the left here. It is narrow so as to fit in the handle. The PIR board is just a prototype board adding into capacitors close to the AM312. The WS2812B strip I place through the acrylic tube and stick it in place. You can also see a 3D printed cap for the acrylic tube, just to clean things up. I used a glue gun with hot melt glue for sticking this together. The handle components are 3D printed, then have M2 insert bolts pushed into them to bolt the PCB onto, also to connect the blade to the handle, and indeed the pommel to the handle. So with my M2 bolts we can connect the PCBs in place, then the blade onto the handle, and the WS2812 LEDs are connected to the PCB. The fully assembled unit looks quite convincing. Without software though, it won't do very much. Let's look at the software stack I used. The WizFi360 Pico board uses the Pico SDK, but of course it has the added chip of the WizFi360 with its own firmware. The driver for this is part of the CMSIS driver library. This uses a CMSIS ecosystem of libraries, and was my first time using these libraries. They did cause me some head scratching. Key here is to use the WIZnet patches and the right version of the libraries. The CMSIS libraries only give a socket connection, not MQTT, directly. Therefore, I chose, as I have done on other projects, to use the free RTOS Core MQTT library to build an adapter for the transport. On top of Core MQTT, I use my own TwinThings library, which provides an IoT framework for pub-sub communication and also for managing digital twin state. This then left a simple application on top, using Forsaken NXG's library for managing the WS2812B LEDs via PIO. A few design decisions. I chose not to use MQTT natively from the WizFi360. This is included in the AT command set, but has limitations on just 3 subscriptions. It's also not included in the libraries for the RP2040, making it a bit too much effort to use. I've chosen not to use TLS or SSL at this time. Once again, TLS is missing from the libraries, and I would need to put this in on the RP2040 side. A task for later, I think. So what does the MQTT space look like for communication? Well, a Saber conforms to my TwinThings framework, so it's able to handle ping to the group all and to the device itself. It also manages its state and uses the get, set and update state topics for this. This is how the configuration will be set up on the device. I want the lamp to be able to turn on all of the lamps together or all off together. I use the group Saber on and off topic for this. I've used some shortened titles here, so GRP is group, TNG is thing, TPC is topic, UPD is update. This is just to save a few bytes, which seemed unnecessary. I'm using the concept of a digital twin to solve a couple of problems in the management of my Saber wall lights. I need to be able to retain the configuration around power loss or resets. I could have saved this to flash memory, but have chosen to instead hold the data within a digital twin service on the network and reload the configuration each time the unit reconnects to the network. The digital twin also gives me the ability to configure all of the Sabers as a group device in one go, rather than load the configuration of each device separately. This is because my twin system understands the concept of groups and queries across groups. So, twins are managed by the Twin Manager, which sits on the MQTT network like any other device. It's actually just a Python running within a Docker service. It also talks to a MySQL database to store the twin state. The database is shared with my MQTT broker, which is EMQX. The Twin Manager can read the authorization table to infer groups from this. The Saber Manager is also a device connected to a broker, again Python within a Docker service. It has an additional browser interface for configuring via a web page. More about that in a bit. So the Twin Manager operates through a group level topic to get or set the values of a set of one or more devices. The results are published to the RES or result topic. So I can set all of the Sabers to turn on and be white for daytime blade color using this payload to the Saber Twin set topic. The Twin Manager can control which attributes are brought back. It can rename those attributes in the return set. It can also query based on attributes in a simple or compound query structure. This is a bit like SQL. This makes management of a set of devices much easier. This is exactly what the Saber Manager application does. Oh yes, it uses LCARs as the graphic user interface. Thanks to Joan Wisenborn for work on the LCARs look and feel. So let's look at a demo of the Saber wall light. We can animate the turn on and off as a Jedi in blue or green, or the dark side of red. But I prefer the Pride Rainbow Saber, just to prove this is an RGB device. We can animate as a spark ignition, or just as a wand shooting, or perhaps it's red alert. And what's better than one Saber wall light? Well, 3 Saber wall lights. If you enjoyed this video, then please do hit like and subscribe. If you want to understand more about this project, well, it's based on the foundations in my Udemy courses. So using Pico for C and C++ development with a good development environment, so you don't spend too much time having to fiddle. WS2812Bs and animation of these LEDs I show in my microprojects course. As soon as you open the door to IoT, you really do need a real-time operating system. I've chosen FreeRTOS for this project, and my FreeRTOS Raspberry Pi Pico course covers this. Along with my growing collection of Pico-related courses, I also have courses on technology strategy for the IT department and data strategy. I post my projects on social media under the name Dr. John EA, along with blogs on IoT, microcontrollers, and corporate IT. Please do follow me. But of course, please like this video and subscribe to my channel.